let's kind of revisit some topics you probably learned in middle school and as recently as chemistry class. You'll see right here the Bohr model of the atom. Now, this is from about 100 years ago. And here's the thing, if you could get a super microscope and zoom into an atom, you would not see this. This is just a model. In real life, all these particles are not like little balls circling the nucleus. It's more smeared out and blurry. It's way more complex. But we use this because it does a really good job of explaining what we need to explain. So I imagine most of this is just review. So an electron. An electron is a negatively charged particle. You also know a proton is a positively charged particle, and a neutron has no charge. Okay, so let's take a look at the atom at the top of the slide. At the center of the atom, you have the nucleus. Now, the nucleus has protons and neutrons. Now, these are very tightly packed, and it's not impossible, but they're pretty much they really don't separate unless you have something like a nuclear fission. That's a nuclear reactor, and that releases crazy amounts of energy. But really, in real life, protons and neutrons in regular life, they just stay put. And you also have the electrons orbiting in their shells. Now, what's kind of really important here are not the first few levels of electrons, it's really the outer electron. These are the valence electrons. Now, these valence electrons, especially in conductors, are free to move. They can kind of jump atom to atom to atom, and this is what allows electricity to flow. More on that later though. Okay, so another thing that you probably learned is opposites attract and likes repel. So let's say we have an electron and a proton, you know, or, simply put, negative charge and positive charge, What would happen is they attract, and if you kind of just reverse the, orientations, it's really the same thing. They're going to attract. Furthermore, if you put positive charge and positive charge next to each other, a proton and a proton, they're going to repel. And of course, an electron and an electron next to each other, or just negative charge and negative charge, again, they repel. They're just like magnets, north and north versus north and south, etc., etc. So charge behaves very similarly to like magnets repelling or attracting or whatever. Okay, take a look at this setup right here. You just see two metal spheres, basically metal balls next to each other, and they are neutrally charged because they have the same number of electrons as protons. So you can see the left sphere A has what, 5 electrons and 5 protons. So the positive and negative charges cancel out. The same thing for B. So since they have no net charge, no overall charge, we say the charge in both of them are zero. And it's kind of interesting how we use Q for charge. You would think it's C, but it's actually Q. Okay, so let's say for whatever reason, an electron moves from sphere A to sphere B, like so. Now, sphere A has more protons than electrons, and sphere B has more electrons than protons. So we say sphere A has a charge of plus 1e, and sphere B has a charge of minus 1e. Now, E is the charge of a proton or electron. An electron is a negative E, that's its charge. A proton is plus 1e. So we just use the letter E for like 1 unit of charge for an electron or proton, and it just depends if it's negative or positive, if it's an electron or proton. So if we move, say, another electron, sphere A has two more protons and electrons, so the charge is plus 2e. Now sphere B has an excess of electrons, more electrons than protons, so we say the charge is negative 2e. So one big thing you may have noticed that protons never move. Unless you're doing like nuclear reactions and nuclear fission, protons you stay put in their atoms. They don't move. So protons stay put. It's only the electrons that move. And you create negative charge or positive charge just based on whether you have extra electrons or a lack of electrons. So it's really the whole name of the game here in electricity is the electrons moving. Okay. So you can see that conductors easily move electrons, but on the other hand, you may have heard of an insulator. So these insulators right here, they could be, plastic spheres or rubber spheres or really anything that's not metal. I mean, they could be wooden. So right now they have an equal number of protons and electrons. They have a no net charge, no net overall charge. Now if I put, say, 5 extra electrons on sphere A, what's going to happen is the charge on sphere A is going to become negative 5e. But on sphere B, it's still 0. Now, here's the thing. Those electrons on sphere A, they can't move because electrons cannot easily move on an insulator. So electrons can easily move on a conductor, like metal, but on an insulator, plastic, rubber, wood, things like that, it really can't move at all. They're kind of like stuck. So if we kind of compare and contrast conductors versus insulators, a metal sphere versus, say, a balloon, if I put these electrons, how many are there? 7. If I put these 7 electrons on the conductor sphere, the metal sphere, what's going to happen is since like charges repel, they're going to repel each other and kind of equally space each other out. There are protons here, but I'm just not showing it. We don't really need it. So when you place electrons on a metal sphere, they're going to try their best to spread apart as equally as possible. And it will happen like nearly instantaneously. It's going to happen in like a millionth of a second. But if I put charge on a balloon somehow, it's just going to stay put. And for example, if you get a balloon and you rub your hair, eventually, you're going to charge the balloon. And that static electricity, that charge is called static because the static electricity just stays there. It doesn't move, you know. So that's why we call it static. It just stays in place. And you can actually kind of feel the charge on the balloon, and it stays put for a good amount of time until it kind of dissipates in the air due to humidity. Now, in the wintertime, especially the wintertime because the air is so dry, it works really well. And say you're walking across the carpet. Well, when you're walking across the carpet, you're literally ripping electrons off something. And say you're ripping it off the carpet. So as you're walking across the carpet, you are accumulating, say, extra electrons. So as you're accumulating extra electrons, we say you are negatively charged because you have extra electrons. Now, if you touch a doorknob, you get that quick zap. And what's kind of happening is all those extra electrons kind of stored on you is going through the doorknob, down the door, into the earth. So that is, you're being charged. It's not exactly like charging a battery, but similar. Now, another way that can happen is when you're walking across a carpet, it could go the other way. You know, the carpet could become negatively charged. So instead of electrons going from the carpet to you, your electrons go from you to the carpet. So since you're lacking those electrons, you are positively charged. So, and it really depends on the material. Like which way is like, do the electrons go from the carpet to the person or the person to the carpet? It really depends on the material, whether the person has rubber soles or I don't know, wooden soles, I guess. So it really depends on the material. But when things are charged, it's really due to the flow of electrons. Another way you can charge things, walking across the carpet or rubbing your hair on the balloon, that is, you're literally, two things are in contact with each other. That is charging by, conduction. Whereas, kind of another way you can charge you is by induction. Induction happens even though it's not directly touching. So let's say we have two metal spheres, the protons are not there, but let's say the metal spheres are neutrally charged. I bring some object, some charged object, close by, you know that electrons repel. And what's going to happen is that charged object that we brought near is going to basically repel all those electrons in sphere A into sphere B. So what happened is, since sphere A lost all those, electrons, not really lost, charge is always conserved, it just went to sphere B. What we can say is those 5 electrons went to sphere B. So sphere A has negative 5e, and since sphere B gained electrons, it's plus 5e. So that is an example of charging by induction. It doesn't actually need to touch, So that is a little bit on electric charge. More in the next